Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be doing an example of the Fourier transform, specifically doing the Fourier transform of the unit impulse function, where in this video we're going to take this generic impulse function a delta t minus t naught, where my function is equals to a for t equals to t naught and 0 otherwise. And essentially, we're tasked with finding this Fourier transform capital X of omega of my function x of t, where capital A and t naught are real constants. And what I normally do is I encourage the viewer to pause the video, try and solve it on their own, and then come back to the video and see if you got the right answer. Okay, so let's go ahead and solve this problem now. And what we can say for our solution is that we know from our past video that our Fourier transform x of omega is equated to the integral from negative infinity to infinity x of t e to the minus j omega t dt. Therefore, in this example, we get that this is equated to the integral from minus infinity to infinity a delta t minus t naught e to the minus j omega t dt. And what we can do is we just pull out that a and say that this is a integrated from negative infinity to infinity delta t minus t naught e to the minus j omega t dt. So now there's two ways which we can solve this problem. And on this slide, I'm going to do the first method, and then the next slide, I'm going to do the second method, where the first way or the first method is by using what we consider the equivalent property and what we consider the shifting property. Where all the equivalence property tells us is that if you have an x of t times a delta t minus t naught, so consider a random function, all right, x of t, let me say it looks something like this, times my Dirac function or my delta function. Again, this is in t and t. The only thing that's going to come out of my x of t is x of t at t naught, right? X of t when t is equals to t naught, and then times delta t minus t naught. So essentially, this is going to be equated to my x of t value. So just to be specific, if this is t naught and this is t naught, this value here, let me say if it's 5, that's the value here that's going to come out, right? The rest of everything else will be 0. So essentially, this is true for all t. And now the shifting property tells us that the integral of negative infinity to infinity of a random x of t times my delta function t minus t naught dt is equated to, again, we can just take out x at t is equals to t naught. So this becomes negative infinity to infinity x at t naught delta t minus t naught. Again, we're using the equivalence property in this situation, dt. So then this here is just a constant, right? So we talked about it maybe being like a 5 or a regular constant. So then we could pull it out. So then this becomes x of t naught integrated from negative infinity to infinity delta t minus t naught dt. If you integrate the delta function from negative infinity to infinity, you will just get 1. So essentially, this becomes x of t naught. Long story short, the shifting property says that if you were to integrate a value x of t by the delta function, you will just get that value x of t at t is equals to t naught. So how can we correlate it to our x of omega? We can say then that x of omega is equated to a integrated from negative infinity to infinity delta t minus t naught e to the minus j omega t dt. If we want to correlate this equation to this equation here, I can easily say that delta t minus t naught is located here, and my x of t is this e to the minus j omega t. So essentially, I hope we can all see this. Using the equivalence and shifting property, we can equate this to a times e to the minus j omega t naught. And this here is your answer. But let's go ahead and rewrite in a more clean manner. So I can say that if x of t is equated to a times delta t minus t naught, or my unit impulse, the continuous time Fourier transform is going to be a e to the minus j omega t naught. And then this is equals to x of omega. And a standardized one that you normally see in textbook is for a is equals to 1 and t is equals to 0. X of t is equals to delta t, where again, this continuous time Fourier transform is simply going to be 1, which is equals to x of omega. So now the second way to do this, which again can be intuitive, is say that if we multiply this by this, basically using the equivalence property, everything is 0 except for at e to the minus j omega t naught. So therefore, I say that x of omega is equated to a integrated from negative infinity to infinity delta t minus t naught e to the minus j omega t naught dt. Again, this is equated to a e to the minus j omega t naught integrated from minus infinity to infinity delta t minus t naught dt. Because again, this is just a constant, so I can pull it out. And this is equated to a e to the minus j omega t naught times the integral of my Dirac function is just 1. So this just becomes 1. So again, I get that a e to the minus j omega t naught. And again, just to keep formalities, let me rewrite that. Therefore, x of t equated to a delta t minus t naught. The continuous time Fourier transform becomes a e to the minus j omega t naught, which is equals to capital X of omega. And when a is equals to 1 and t naught is equals to 0, x of t is equals to my Dirac function, delta t, and the continuous time Fourier transform is just 1 equated to capital X of omega. Okay, if you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. If you liked the video, please give it a thumbs up, and please share the video to your colleagues and friends. Lastly, if you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.